All right, so today I'll talk about the density increment method. Okay, so this is a now standard technique that can be used to show density bounds on sets lacking arithmetic configurations. So it originates in Roth's proof of his theorem on three-term arithmetic progressions, even though he didn't phrase it in exactly this way. He phrased it more, I guess, as a downward induction. We are going to use it to show a theorem called the Furstenberg-Charcosy theorem. So this was proven by Furstenberg in 1977 in the same paper in which he gave his ergodic-theoretic proof of Zimriti's theorem, and then also by Charcosy in 1978 via Fourier analytic methods. Okay, so this theorem states that if A is a subset of the first n integers and it has no non-trivial two-term arithmetic progressions x plus y squared, so non-trivial, y can't be 0, then the size of A is little o of n. Okay. So Furstenberg's proof gave no effective bounds in this theorem, but Charcosy's proof lets you save a power of log. So Charcosy proved a bound of like A is at most n times log n to the 2/3 divided by log n to the 1/3. Okay, so the proof we'll present is actually due to Green, Tau, and Ziegler, and it's called the Fourier free proof. Yeah. Where? So this is supposed to be like two-term progressions with. So this is like square differences. It's not the nonlinear Roth configuration. So the proof we're going to present of it using the density increment method is called the Fourier free proof. And it gives a weaker bound. So this gives like size of A is at most n over log n to the 1/4. So this proof is more elementary, as its name suggests. It uses no Fourier analysis, and it also uses ideas that will be like more relevant to us when we prove the nonlinear Roth theorem. Okay. So the density increment method consists of if you assume that a set has no non-trivial copies of some configuration, then you have some lemma called a density increment lemma that says, in this situation, you can find a long arithmetic progression on which your set has increased density. And then if you're in that situation, then you can rerun the argument like relative to the arithmetic progression on which you have increased density, and further like increment the density, but at some point, this like density can't go above 1, and so then this argument fails. And you're able to rewind the argument to obtain a bound on the size of your original set. So what we'll precisely prove in this situation is okay, so let's say that A is a subset of the first n integers that has density alpha and no copies of the configuration x plus y squared, which let's call star. some non-trivial square differences. Okay, so then either n must be small, so n is bounded above by some constant times alpha to the negative 64, or there exists an arithmetic regression with base point A and common difference Q of length m that's at least, say, a constant times n to the 1 over 16, such that A has density at least alpha plus alpha to the 4th over 4 on this progression. So such that the size of the intersection with the arithmetic progression, A plus QM, or sorry, this will have common difference Q squared M, with M size up to M. So this is at least alpha plus alpha to the 4th over 4 times M. Okay. All right, so this is what I mean by increased density. Okay, so then the idea of the argument is that, okay, either you're in this case in which you know that then alpha must be at most like a constant times n to the 1 over 64, and then you're happy. If not, you're in the second case, and you have increased density on a long arithmetic progression with square common difference. So then you can rescale this intersection and then get a subset, let's say A prime of M, with density at least alpha plus alpha to the 4th over 4, that again lacks non-trivial square differences. And then you can iterate the argument, and you can't iterate it forever because you increase the density by at least alpha to the 4th over 4 at some point, or at every point. So then at some point, the largeness assumption on n must fail. So n must be small compared to your alpha I. And then you can rewind that, like I said, to get a bound on the density of your original set A. Okay, so we'll see that after we prove this. Okay. All right, so for the proof, let's let f sub A be what's called the balanced function of A. So that's going to be the indicator function of A minus its density alpha times the indicator function of the interval on which A lives. Okay, so note that this has mean 0. It's one bounded, and it's supported on the first n integers. So then since A has no square differences, so it's free of the two-term progression x plus y squared, then the following average that I'm going to write down will be 0. So I'll write it down and then explain why I wrote this particular thing down. The average over x, the first n integers, the average over y of size up to n to the 1/4, the average over z, integers up to n to the 1 over 16, of indicator function of A at x, indicator function of A at x plus y plus z squared, then this is 0. Okay, so first of all, this is 0 because x plus y plus z squared. So since y and z, their intervals both start at 1, this would be like a non-trivial progression x plus y squared. So then certainly this average is 0 because A contains no copies of this configuration. But you'll see I'm not averaging over like intervals of like the maximum size that I can average over for A in the first n integers. And I've restricted the ranges of y and z so that I'm free to change variables in x and not incur like, and basically just incur like negligible error terms. So you could take like actually y and z to be like n to the like 1 over 100 and then n to the like 1 over a million or something. The same argument will work, but you'll get a worse bound there, or a worse exponent. Also, so I'm writing things like, okay, this is the interval of integers from like 1 up to n to the 1/4. So you can either assume that when I write this for like a number that might not be an integer, then I'm just taking the floor of it, or you can assume that I've picked n to be like a 16th power or something. All right, so since we've now written a, or the indicator function of a, as the sum of its balanced function plus alpha times the indicator function for n integers, we can write this average as the sum of two averages, one where the second function is replaced by the balanced function, and the other where the second function is replaced by alpha times the indicator function of the first n integers. So the average above this equals the sum of, so the first one I'll call A. So this will be same average, but with indicator function of A, and then balanced function. And the second term will be the same, with this replaced by alpha times the indicator function of the first n integers. So let's consider the second of these two averages first. So let's note that if, as we have here, y is an integer that's at most n to the 1/4, and z is an integer that's at most n to the 1 over 16, then, okay, like y plus z squared. Okay, this is going to be like on the order of at most like n to the 1/4, so then its square will be on the order of square root of n. Okay, so then that means for like any fixed y and z in these intervals, the value of this indicator function at x plus y plus z squared is like not equal to 1, so it's equal to 0, for only on the order of at most like square root of n choices of x. So then the contribution of like those choices to this average is bounded above by like big O of like 1 over square root of n. Okay, so what we get is that this b equals alpha times the average for x y and z of the indicator function of a of x, because we can replace this function with just the constant function 1 at the cost of an error of 1 over square root of n. Okay, so the average over z now does nothing in this average. The average over y now does nothing. And then we're just averaging over x up to n. So then this average equals alpha, the density of a in the first n integers. So then this whole expression equals like alpha squared plus this error. All right, so what this means is that we have this average that's 0. That's the sum of the first average A and the second average B. And the second average B is alpha squared plus some error. So if n is large, then the error term will be small. And so this average will be like kind of large and positive, which means that for this average to be 0, this average A must be negative of large magnitude to cancel out the contribution from B. So what we get is that the average A must have magnitude at least alpha squared plus big O of 1 over square root of n. Okay, so then what that means by the triangle inequality that, so applying the triangle inequality here, so I'm going to apply it, I'm going to put the bars like there and there. So then we have that the average over x, average over y, then absolute value bar, and average over z, of balanced function, x plus y plus z squared. This is at least alpha squared plus big O of 1 over square root of n. So now I'm going to Cauchy-Schwarz. And so last time we saw that the Cauchy-Schwarz inequality is useful for kind of like mixing progressions to get configurations that are like more and more equidistributed. Another use of the Cauchy-Schwarz inequality is to take derivatives. So I have a quadratic polynomial here. I'm going to apply the Cauchy-Schwarz inequality and then make a change of variables to basically like differentiate this polynomial to get a linear polynomial. Okay, so now we apply the Cauchy-Schwarz inequality. So then that's going to have the effect of squaring this and then also squaring I guess the right-hand side. So we have the same average over x and y. Then we square the average over z. And this is going to be at least alpha to the 4th plus big O of 1 over square root of n. Okay. So now I'll expand the square and do like I said and make a change of variables. Okay. So expanding the square. So if we expand this square, then we'll get 2 copies of the variable z, and then 2 copies of this function. So that gives us that the average over x, average over y, actually to fit everything, put the average over y under the average over x. Now we're going to get an average over z and w, which will be the second copy of z, to n to the 1 over 16. And then we'll get our 2 copies of the balance function. So note that like the balance function being the indicator function of a set, like minus the density times the indicator function of another set, this is real valued. So I don't need to put complex conjugates over anything. So then I get balance function of x plus y plus z squared balanced function of x plus y plus w squared. All of this is at least alpha to the fourth plus the error term. Okay. So now what I want to do is change variables in x. So subtract y plus c squared from both of these instances of x. But I have to be a bit careful because this average is restricted to x over just the first n integers. I don't have like a sum over the entire group. But I can rectify that by like inserting in an indicator function of the first n integers. So we can write okay, so this is an inequality where like this thing I wrote on top is the left-hand side. So the left-hand side as, so also swapping the order of summation, average over y, average over z and w. And then the average over x is going to become the sum 1 over n times the sum over x in all the integers, indicator function of the first n integers. Okay, now I've run out of space. Okay, then balanced function x plus y plus z squared, indicator function, or sorry, balanced function of x plus y plus w squared. And now I can change variables in x. So we make the change of variables. Okay, this yields I think I'll leave up the density increment lemma statement so I don't have to write it again. Okay, so if we make the change of variables, x maps to, oh, I didn't say what the change of variables is. So now this yields okay, we have the average over y, the average over z and w, and this 1 over n times the sum x over all the integers of indicator function of the first n integers, x minus y plus z squared, and then balanced function of x, and then balanced function of x plus y minus, or no, x plus y plus w squared minus y plus z squared. Okay. So the first thing to note is for any fixed y and z, so y up to n to the 1/4, z up to n to the 1 over 16, again, y plus z squared is going to be of size like at most square root of n. So the number of points x at which the indicator function of x minus this square differs from just like the indicator function of x is on the order of like at most square root of n. So then we can replace the indicator function of n evaluated at x minus the square of y plus z with just the indicator function of the first n integers evaluated at x at the cost of an error that's at most 1 over square root of n. Okay, and also we can expand these squares and then do the subtraction. So we get that this equals, so if this is replaced by just indicator function of x, then we get our average over x back. We have the average over y, average over z, and w. Balanced function evaluated at x, and then balanced function evaluated at x plus, we get like 2 w minus z times y plus w squared minus c squared. Okay, all of this plus the error that came from changing variables. Right. Okay, so now now we are pretty happy. We're close to being able to get a density increment. Right. Yeah, so now we'll just apply the triangle inequality one more time. Oh yeah, and so note here, like now we've done the differentiation of the polynomial. Now we have some linear polynomial in y when we started with a quadratic polynomial in y. So we had that, okay, this left-hand side was at least alpha to the quarter plus some error. And now we've shown that that left-hand side equals this quantity plus an error of the same size. So applying the triangle inequality to get rid of this first balanced function, get that the average over x, average over z and w, an absolute value of the average over y, balanced function at x plus 2w minus c y plus w squared minus c squared. Okay, this whole quantity is at least alpha to the 4th plus an error that's at most 1 over square root of n. Okay, so yeah, the thing to note now is that this interior average is the average over an arithmetic progression with common difference 2 times w minus c. So what this is telling us is that the average of this balance function locally over arithmetic progressions with relatively small common difference is biased. So this is a thing with mean zero. Somehow its average locally over these progressions is pretty large. But we don't know yet, like, or we have to argue that this isn't because the set A has like decreased density on all the arithmetic progressions modulo 2 times w minus c. Okay. All right, so we're gonna now want to apply the pigeonhole principle to fix z and w. We also maybe want to clean this expression up a bit by subtracting the w squared minus z squared. So we can again make another change of variables by doing the same sort of maneuver we did when we made the first change of variables. To get that, if we make the change of variables the change of variables x maps to x minus w squared plus z squared, then again we'll introduce an error actually smaller than this big O of 1 over square root of n, because w squared minus z squared is on the order of, at most, like the 8th root of n. We get that our average for x, average over z and w, then the average over y, of balanced function x plus 2 w minus z y, this is large. Okay. So now we want to pigeonhole to fix w and z, but we want to make sure that the progression has a non-zero length, or non-zero common difference, which I guess, okay, also, okay, maybe it would be length 1 then, if it had 0 common difference. But note that the contribution to this average coming from when z equals w is, okay, so how often does that happen? So we have like n to the 1/8 possible like choices of pairs, and the number of times where they're equal is like n to the 1 over 16. So then we have like n to the 1 over 16 divided by n to the 1 over 8, or 1 over 8. So then the contribution to this average coming from when z and w are the same, this is at most 1 over n to the 1 over 16. Okay, so we can restrict to the case where they're distinct at the cost of an error on the order of 1 over the 16th root of n. And changing this normalization here also introduces an error of at most 1 over n to the 1 over 16. This whole average is at least alpha to the 4th plus big O over 16th root of n. Okay, so now we can apply the pigeonhole principle. So that means there's some choice of z not equal to w in this interval such that the average over x of the absolute value of the average over y for this fixed progression is large. All right, so by the pigeonhole principle, there exists distinct z and w in the interval such that setting q to be to w minus z, the average over x, the average over the arithmetic progression starting at x with common difference q and length n to the 1/4, the balanced function. This has size at least alpha to the 4th plus some error. Okay, So this says that our original set A is biased on arithmetic expressions with common difference q and length n to the 1/4. But like I said before, like it's possible that somehow it has like lower density than alpha on like a bunch of these. And so we can't deduce a density increment. But it turns out that this is like not the case because the density of A overall in the interval is alpha. So here's how to use that rigorously. Okay, so we now note that if we take the same average without the absolute value of r's, okay, what do we get? So, right. This, for each fixed x, so now we do another one of these changes of variables to introduce a small error. So if we do x maps to x minus qy, then since q times y is on the order of like n to the 5/16, if we make the change of variables, x maps to x minus qy in this average, we introduce an error of size at most 1 over n to the 11/16. Okay, so this equals the average over x average over y, the balanced function after the change of variables, plus the error. Okay, so now this average over y does nothing, but then we have the average over x of the balanced function, which, as I said at the beginning, has mean 0. So this whole quantity has size at most something on the order of 1 over n to the 1 over, or n to the 11/16. Okay, which you'll note is like much smaller than the error that we already have. Okay, so now what we do is we'll use the following identity. So we'll use that. If you take r plus the absolute value of r divided by 2, then this is the maximum of 0 in r. So it's 0 when r is negative and r when r is positive. This holds for all real numbers r. So then we add this expression and then this expression without absolute values. So taking like this quantity, the average over y, to be r, to get that and dividing by 2, the average over x of the maximum of 0, the average over y, this is at least alpha to the quarter, or alpha to the 4th, plus our error. Okay, so now we're almost done. So this says that we have increased density. So basically here we could almost apply the pigeonhole principle and then get that we have increased density on the arithmetic progression with common difference q, starting at x of length n to the 1/4. But the issue is here for like some of these x, that arithmetic progression might not lie totally in the interval from 1 up to n. But that's only an issue when x is like less than or equal to like 2 square root of n, or greater than or equal to like n minus 2 square root of n. Okay, but the contribution to this average coming from those x is even smaller than this error term. So it's on the order of 1 over square root of n. That says that, okay, we can throw those out and then apply the pigeonhole principle and get that there exists, by pigeonholing again, there exists some x that's at least 2 square root of n, and at most n minus 2 square root of n, such that the average for y, the balanced function, x plus over the progression x plus qy, is at least alpha to the quarter plus the error term. Okay. All right, so because of our choice of x ensures that this arithmetic progression always lies in the interval from 1 up to n, we can use that the balanced function is the indicator function minus alpha times the indicator function from 1 up to n to get that. So this left-hand side equals the size of A intersected with the arithmetic progression, x plus qy. Minus alpha. Okay. So this gives us a density increment. Okay, so now we've given a name to our progression. What we have is that A has increased density on P. Okay. So this is almost what we want, but the issue is we wanted. Oh, thank you. Yeah. That would be worse than trivial. Thank you. So this is like almost what we want, except we wanted a square common difference, and we just have Q here. Also, I said, okay, I want like Q to be positive, but note that if Q were negative, we could reparameterize the progression. So you can either, if you have a progression x plus y up to x plus k minus 1 times y, you can either view this as a k-term arithmetic progression with common difference y starting at x, or a like k-term arithmetic progression with common difference negative y starting at like x plus k minus 1 times y. Okay. But what was important and why we did some of this maneuvering was that Q is non-zero. Okay, so without loss of generality, Q is positive. Okay, Now to get the same statement, but with q replaced by q squared, we need to further partition the arithmetic progression p into subprogressions and then pigeonhole once more. And then we're truly done. Now partition p into, let's say k being, so what I want to do is so p is an arithmetic progression with common difference q. So I want to split that arithmetic progression up into congruence classes modulo q squared. So that splits it up into q different progressions. But then those will have length on the order of n to the 1/4 divided by q. But what I actually want is for them to be shorter for pigeonholing reasons. So I'm going to partition this progression into q times. So I'll take n to the 1/4 over q. Progressions that'll be of length n to the 1/16. So it'll be this many. Full progressions. Arithmetic progressions of length, let's say m equal to n to the 1/16, plus some junk left over. Okay, so I'll call them I1 up to IK, plus, if we have stuff left over in each congruence class modulo q squared, we'll have at most q arithmetic progressions left over, j1 up to jl, of length strictly less than m. Okay, and then the contribution to the size of A intersect P, coming from these bad progressions J, will be negligible. Okay, so the contribution to size of A intersect P, maybe I'll index the i's by j's and the j's by I. Coming from the j's. Okay, so coming from this is, what is that? So that's at most the total of the sum of the lengths of all these intervals. So it's at most L times M, but L is at most Q. And M, so Q is at most n to the 1/16. M is at most also n to the 1/16. Okay, so this is at most n to the 1/8. Okay, but this has size on the order of n to the 1/4. Okay, so that's negligible. So then by pigeonholing, once again, there exists an J, oh, and J, no, AJ, such that IJ intersect A. So again, so when we do the pigeonhole, we're also dividing by Q. So then IJ intersect A divided by M will have density at least alpha plus alpha to the quarter. Alpha to the 4, 1/16th root of n. Okay, so now, okay, did I forget to write? I forgot to write the most important thing, that these progressions have common difference q squared. Okay. So now this is basically almost the statement we want. So now note that if n is sufficiently large, so at least as large as c over alpha to the 64, for c some large enough absolute constant, then this is the right-hand side, is going to be at least, oh, sorry, there should have been a dividing by 2. Okay, that's divided by 2. That's divided by 2. And this is divided by 2. Okay, so now this will be at least alpha plus alpha to the 4th divided by 4. So if you pick n large enough, then you can make this error term less than like alpha to the 4th divided by 4. All right, and so now we're done. Okay, because either n is at most some constant divided by alpha to the 64, or else we have the density increment we wanted. Okay, okay, I have 5 minutes left, so now I'll tell you how we use this lemma to prove the Furstenberg-Sarkozy theorem. Okay, this is fortunately fast. Okay, so while I erase, I'll also say that in the exercises, I've put some basic Fourier analysis stuff that we'll use in the second 2 lectures. So if you haven't seen it before, I have some exercises to verify some basic properties, the Fourier transform, and also to prove a case of Weil's inequality, which is a statement about exponential sums. Right, so now we will actually do a density increment argument, do the proof of Furstenberg-Sarkozy theorem. Okay, so the key thing to note here is that if we let P be any arithmetic progression with square common difference, okay, so then if A has no non-trivial progressions x plus y squared, then the rescaled set, A prime, which will be taking the intersection of A with P and then translating it to the origin and dividing by Q. So this will be all M such that M, or A plus QM, is in A intersect P. This also contains, oh yeah, thank you. Yeah, definitely need Q squared. Then this contains no square common differences either. Okay, and the point is that if x plus y squared is in the rescaled set, then just by definition, A plus QX and A plus QX plus Q squared, sorry, all the Q's are squared, A plus Q squared X, A plus Q squared X plus Q squared Y squared. This is also of the form x plus y squared, where now y is q times y, and x is a plus qx squared. And note that y is 0 if and only if q times y is 0. So if A is free of non-trivial progressions, then so is A prime. And we can use this to iterate this lemma. Okay, so let's suppose that A is a subset of the first n integers, and it has density alpha, and no non-trivial square differences, x plus y squared. Okay, so then let's set A naught to be A, n naught to be n, and alpha naught to be alpha. And now we apply the lemma repeatedly as long as ni is large, so at least as large as whatever our constant is times alpha to the negative 64, to get a sequence ai, ni, and alpha I with, first of all, ai contained in the first ni integers, ai having density alpha I in the set, and then what we get from the statement of the density increment lemma, that alpha I is at least alpha I minus 1 plus alpha I minus 1 to the fourth divided by 4, along with a lower bound on ni. So ni will be at least n to the 1 over 16, or I minus 1. Okay, but so note that because of this relation, the alpha i's are increasing, or actually strictly increasing. And so you get a density increment of at least our original alpha to the fourth divided by 4 at each step. And so since density can't go above 1, this iteration must terminate whenever, or at some point, when I is at most like alpha to the fourth over 4. And then at that point, this largeness assumption must fail. Okay, so we get that this terminates for some I below 4 over alpha to the fourth, at which point we must have n to the n sub I being at most some constant times n I minus 1, alpha, 1 over alpha I to the 64. Okay, but like the alpha i's are increasing, so this is at most our original alpha to the negative 64. But on the other hand, we have a lower bound on n sub I coming from the second property. N sub I will be at least n to the 1 over 16 to the I, but then I is at most 4 over alpha to the fourth. So be n to the 1 over 16 to the 4 over alpha. Okay, so if we combine these, we get n to the 1 over 16 to the 4 over alpha to the fourth is at most some constant times alpha to the negative 64. So now all one needs to do is to take double logs of both sides. And then you can rearrange, and this will tell you that alpha is at most 1 over log n to the 1/4, like times some constant. Okay, so I'll stop there.